Hello, welcome back to AP Physics. This unit is on circular motion and universal gravitation. So we're going to start off with circular motion, things going around in a circle. Whenever something is rotating, there is what's called the axis of rotation, and it's a line that goes through the object of which the points aren't moving. It's the line at which it's spinning about, basically. So in a record spinning around like so, the line would just go through the center of the record, perpendicular to the surface of the record. So points on the axis of rotation appear to be stationary. They have the least velocity per se, and so notice it looks much slower in the middle. Now, if the axis of rotation doesn't have to be in the center of an object, you can force an axis of rotation by pinning it or something like that and making it spin about that point. A little side note here: when the axis of rotation goes through the object, it's called rotation. When the axis of rotation is outside of the object, it is said to be revolving. So it might be a multiple choice question along those lines, but not a big deal. So the Earth both rotates and revolves. It rotates, which causes the 24 hours in a day, and it revolves, which causes the 365 days in a year. So it both rotates and revolves, but it does so at the same time. So, all right. Now, the time it takes for an object to complete one rotation is called the period. The symbol for the period is T. T for time, makes sense. And what do you think we're going to measure period in? Probably seconds, and that is the unit. So if you were to start your stopwatch when we started the object and stop it when it reaches back to the line, you would measure the period. So you would start your stopwatch and then let it go around and then stop your stopwatch, and that would be T. That would be the period, whatever that is in seconds. So if we were to look at an object traveling in a circle, would we say this particular object, would it have a constant speed? Does it appear to have a constant speed? I think so. It looks like it's about a constant speed. Would it have a constant velocity? Now remember, velocity includes both speed and direction of motion. This object is constantly turning, so its direction of motion is constantly changing, so it does not have a constant velocity. So what we're going to focus on is what's called uniform circular motion, which is an object moving around, rotating or revolving at a constant speed. Okay, the speed and direction of an object as it's traveling around in a circular path is known as the tangential velocity, and the symbol for that is V sub t, V subscript t. And it's called tangential velocity because the velocity is always tangent to the circular path that it's following. So it's always tangent to the circular path. Okay, and this would be measured in meters per second. So it's the linear speed of it in meters per second. If we wanted to calculate its speed, we would need a convenient distance and a convenient time. Well, we would need it, but it would be nice to use. What would be a convenient distance the object travels? What would a convenient distance be? Probably the circumference. Okay, and how long does it take the object to travel around its circumference? The period. So distance over time, the circumference divided by the period. So V sub t equals 2 pi r over t. And so that's your first equation for this unit. So if we were to have two ladybugs and they were spinning on a record, and I would ask which of these had the greater tangential velocity, you would of course tell me that it would be the outer ladybug because they have a bigger circumference to travel in the same period, in the same time. So they travel more meters per second to get around that bigger circle. Now, is this object that's spinning or that's revolving around some mysterious other object, is it accelerating? Yes, it is. Now it's only changing direction. So when if we were to use our acceleration equation, we'd need to take into account direction. That'd be v2 minus v1. So I just look at it at two arbitrary spots. And if I were to subtract v2 minus v1, we would flip v1. So v2 flip v2, so minus v1. We would see that the acceleration vector, the direction of that vector, is going to point to the center of the circle. And an object that's traveling around in uniform circular motion it's accelerating, and its acceleration is called centripetal acceleration. So, and the centripetal acceleration, or a sub c, is always pointed to the center of the circle. Okay, which is why it constantly changes the direction, but it's never changing the velocity because it's always perpendicular to the velocity. It's never in the direction of the velocity to speed it up or opposite the direction of velocity to slow it down. So centripetal means center seeking. All right. So the tangential velocity, which is the black line, and the centripetal acceleration are always perpendicular to each other. Which is why they never speed up or slow down. So the equation for centripetal acceleration is this, just simple, vt squared over r. So pause if you need to. So the centripetal acceleration, the harder you're accelerating, the harder it is to make that turn if you're going around the turn. So what would make it really hard to go around the turn? A, if you were going really, really fast, if you had a high VT, or B, if the radius of that turn was very small, because a small r is going to give you a big A. And so that would basically mean a sharp turn if it has a small turn radius. Simple problem. A drum of a washing machine has a radius of 34 centimeters. During the spin cycle, the drum rotates with a tangential velocity of 5.5 meters per second. What is the tangential acceleration? What's its direction? And what is the period of rotation? So we'll start with A, which is the centripetal acceleration. And so we just use Vt squared over r, A sub c equals Vt squared over r. We do need to convert our radius to meters, so I know we could all do that in our sleep. 34 centimeters equals 0.34 meters, and so square the Vt divided by the r, and you get 89 meters per second squared. What's the direction of that acceleration? It's always to the center of the circular path. And what is the period? Well, we're going to use this equation, Vt equals 2 pi r over t, where our Vt we know is 5.5, 2 pi r is 0.34, and we're solving for the t. And we get that the period equals 0.388 seconds. So just kind of a basic problem. So let's see, we've got two cars. One has a speedometer that reads 60 miles per hour. The second one reads 120 miles per hour. Compare the centripetal accelerations. Well, the tangential velocity is going to be what the speedometer reads. That's the speedometer reading as it rounds the turn. And so this car is moving twice as fast. Since the centripetal acceleration is equal to Vt squared over r, since this has twice the Vt and it's squared, it's going to have 4 times the centripetal acceleration. Now, if we compare two turns, here we've got a larger radius turn, and here we've got a sharper radius turn that is exactly 1/2 the radius of the larger turn. And the speedometer reads a constant 100 miles per hour, so the Vt is the same. But when I have the radius, Vt squared divided by r, when I have r, I'm dividing by 1/2. So that's going to be doubling the centripetal acceleration. So this would require twice the centripetal acceleration as the larger turn. So if we have 2 pennies on a Lazy Susan or on a record, and we send the record for a spin, and we compare the radii. So this penny has twice the radius of turn of this penny. And if we compare their velocities, this penny has twice the velocity of that penny, since it's got twice the radius. So, if we substitute in for vt squared over r, we substitute in 2 pi r over t, and do a little bit of mathematical massaging, we get a sub c equals 4 pi squared r over t squared. That is not an equation you memorize or anything. It's simply two equations mushed together. I would know the v equals 2 pi r over t equation. The a sub c equals vt squared over r is on your equation sheet. So compare the accelerations of these two balls going around in a circle. Well, based on this equation, if this has half the period for the same radius, and this is halved, this is going to have 4 times the centripetal acceleration. 4 times the centripetal acceleration. What is the direction of the net force on the object? So, well, remember, force equals mass times acceleration, and the net force is always in the direction of the acceleration. So, since the acceleration is always pointed towards the center of the object, the center of the circular path, the centripetal force is always pointed to the centripetal to the center of the object. So you've probably heard of centripetal force before, not to be confused with centrifugal force, which is an imaginary force. That force is made up. Centripetal force is always a force that points towards the center of the circle. So the centripetal force is just in the direction of the centripetal acceleration. Now, the centripetal force is not a new force. It's not going to get added to our list of the normal force, force of friction, force of gravity, force of tension. It is not a new type of force. One of these types of forces that we've already talked about is going to be providing the centripetal force, is going to be the centripetal force. So how would this force know to constantly point towards the center of the circle? It must be some kind of magical computer-guided force to always point towards the center of the circle, constantly changing its direction. No, it's not. Okay, normally what I would do right now is I'd take a ball and I'd swing it around on a string, and I'd say, what was the centripetal force? What's the centripetal force of the ball traveling around, being swung around on a string? Well, it's the force of tension. How does the tension always know to point to the middle? Well, because my finger's in the middle, and the string is always going to be connected to my finger. So the direction is always to the middle. And here we've got the Earth traveling around the sun. What's providing the centripetal force in this scenario? Well, it'd be the force of gravity between the Earth and the sun. So again, it's not a new force. It's just one of the other forces that's causing it to travel in a circle. And here we've got one of those rides where you stand up on the ride and it spins you around, kind of like you're on the inside of a washing machine drum. So here, this would be where all the riders are standing up against the wall. What kind of force is providing the centripetal force in this scenario? I assume this is flat. This is an overhead view of it. Well, it would be the normal force that's between you and the wall. The wall is pushing you toward the center of the circle. So it would be a normal force constantly pushing you to the center of the circle. If we have a penny on a record, and it's a flat record, so meaning this is flat on the ground and this is an overhead view, what's providing the centripetal force for the penny as it travels around in a circle? Gravity is into the page, going into the screen. The normal force is coming out of the screen, and those aren't towards the center of the circle. The only force that's to the center of the circle would be the force of friction, and the force of friction would be the centripetal force in this case. So normally what I would do right about now is I'd take my ball on a string and I would swing it around in a circle, and I'd say, all right, if I let go of the string or cut the string right here, what direction would the ball take? What path would it take? Would it fly straight out? Would it fly at an angle? Would it go out and curve? And this is an overhead view. We're in space, by the way. So we're in space. There's no gravity. Would it fly straight to the right? Would it continue the circular path, or would it somehow train in? Well, if we're in space and there's no gravity and the string is cut, there's no force on the tennis ball, which means that we can eliminate any path that's curved because we need a force in order to change our direction. So that leaves us 3. Would it fly straight out, fly off at an angle, or fly off directly to the right? Well, normally is when I would do this, and what you find out is it is D. Why would it travel in D, the direction of D? Because that was the direction it was traveling before the string was cut. And remember, when we remove forces, an object keeps doing whatever it was doing. This is the direction of the tangential velocity. So again, we've got an overhead view of a car going around in a track. What provides the centripetal force for a car that's going around in a circular track? Well, that would be friction. And if friction is lost, okay, if it no longer has that centripetal force, well, it's going to keep traveling in the direction that it was traveling, which on the left side of this would be straight down. So you would go in a straight line path. Now, the net force in the uniform circular motion is the centripetal force. That's something I'm going to want to beat into you. So if an object is traveling in uniform circular motion, the net force is the centripetal force. Any other forces must cancel. We're skipping this. Okay, so since force equals mass times acceleration, F sub c equals ma sub c. So force equals mass times acceleration. Centripetal force equals mass times centripetal acceleration. Okay. Compare the centripetal forces that are going on. Well, I think we already said before that this object, since it has half the period, it's got twice the velocity, and since it has twice the tangential velocity, it's going to have 4 times the centripetal acceleration, and therefore 4 times the centripetal force needed to allow it to go around in that circle. Either if it's a string, the tension in the string will be 4 times greater on this one on the left than it would be on the one on the right. So here we've got equal velocities, and here what we're going to do is compare these two. Which one is going to require the greater force? Well, the greater acceleration is going to require the greater the force. So the velocities are the same. The r's are different, and this one has a smaller r, so which means it's got a bigger a sub c. So this is going to require greater force. Basically, it's making a tighter turn at the same speed. So your car is going to squeal more if you're making a tighter turn. Here we've got another object. So here we've got the same radius, but we have a smaller t. Which one is going to require the greater force? The smaller t is going to make a bigger a sub c. Which one is going to require the greater a sub c? In this case, the a sub c would be the same because it's traveling the same path at the same speed. But since they have different masses, and this one has a greater mass, it's going to have a bigger f sub c, okay, because it's mass times centripetal acceleration. Okay, and that is where we will cut it quits for today.